Hi everyone, so today we're going to talk about inductor arrangements, and this means we're going to look at the series and parallel combinations of inductors, and we're going to also look at what happens when these are in steady state circuits. So just like we did for capacitors, we're going to look at series and parallel and the VI relationships and how they combine when we have multiple inductors in these arrangements. So we'll get started with series arrangements, and as per usual, we have in series circuits a single current flowing through both components. Now what I want to do is I want to replace this with one inductor LT IT, which has the same current and the same voltage. So if I were to describe this arrangement, the VI relationship, I would get IT is equal to LT di dt. So I want to find out what is this L in terms of L1 and L2. So what I'm going to do is I'm going to write the VI relationship for each inductor individually. So V1 is equal to L1 di dt and V2 is equal to L2 di dt. And I know the total voltage across both of them is equal to the sum of the voltages. So I add them up and I get L1 plus L2 di dt. Now if I relate this to my equation, I'll see that LT is equal to L1 plus L2. So that is how we combine the inductors in series. It is the same as how we combine resistors in series. R total is equal to R1 plus R2, L total is equal to L1 plus L2. And of course, if we have more, 10 inductors, 20 inductors, however many they are, we just sum them all to get the series equivalent. Now moving on to parallel, and again just like we did with resistors and capacitors, we know now that the voltage across both is the same, and we have I1t and I2t. Now again, what I want to do is I want to take this and turn it into a single inductor with a single current I, this time capital T for total current, and I want to relate that to some total inductance. So what I'm going to do again is I'm going to write the VI relationships for each one. This time, since the currents are splitting, I'm going to write them in terms of the current. So I1, 1 on L1 integral of V dt, I2, 1 on L2 integral of V dt. And now I know that the total current is the sum of these currents, and I see that IT is equal to 1 on L1 plus 1 on L2 integral of V t dt. Now for my equivalent, which I have here, I would have gotten IT is equal to 1 on LT integral, say from 0 to t1 Vt dt. So I could see here now that the 1 on LT is pretty much 1 on L1 plus 1 on L2. And if I make that the subject of the formula, I'll get LT, sorry, is L1 L2 on L1 plus L2, product over sum. So the same result as we had for resistors. This of course only works for 2, this product over sum. If we want to do it more generally, we should have 1 on LT is equal to 1 on L1 plus 1 on L2 plus 1 on Ln. So this is the general form. This product over sum only works in the case of 2 inductors or 2 resistors or 2 capacitors as it was before. Remember though, for the capacitors, the parallel arrangement, you add and not use this product over sum. So let's look now at the DC response, just like we did with capacitors, we're going to look at what happens when the variables are constant. So we have the voltage here and we have L di dt. Now in DC, we have constant variables, so we have a constant I. Since I is constant, di dt goes to 0 and Vt goes to 0. Now if I have an inductor and the voltage across it is 0 volts, that means it's essentially a short circuit. So if I look at this in terms of my circuits, just like I did with capacitors, wherever I have an inductor, I could now replace it with a short circuit. And when I replace it with a short circuit, then I could go about my normal circuit analysis. So in this case, I have the inductor cross this resistor. When it becomes a short circuit, it short circuits the 10 ohm resistor. And then I just have 12 volts over 7 ohms. So that will be my current. So if I have mixtures now of capacitors and inductors, I just have to substitute them for open circuits and short circuits, as the case may be. And then I go about solving the DC circuits in the normal way. Remember again, this is only for steady state. We're going to look at the transient response in a little while, but when it comes to the transient response, we don't do this sort of substitution. This is only for steady state. So next time we will look at, well, this time we looked at the series and parallel combinations and solving with steady state, solving the steady state circuits when there are inductors in them. And next time we're going to look at transient. So we've been talking about this, that some of this analysis holds only for steady state circuits. So we're going to start to look at what does it mean to be transient and how does that change our analysis.